yesterday we looked at the atomic spectrum, remember, of the different elements, okay? So today we're going to talk about that real quickly before we get into electron configuration, okay? So that was the electromagnetic spectrum, just reversed from the way we looked at it in the flips lesson. So remember, each element has its own unique electron configuration, which is what we're going to learn here in a second. But because of that unique electron configuration, whenever the electrons are excited or they absorb or release energy, the photons that are, released have a unique series of energy lines. We call that atomic spectrum. Okay. Within the atomic spectrum, you can have the emission spectrum, which shows the wavelength of light that is released when they are going back down to their ground state. Because remember, they absorb energy, jump up to the excited state, they release that energy in the form of a photon, and fall back down to the ground state. Okay, so that's the emission spectrum. The absorption spectrum is the absence of the wavelengths of light that are absorbed by the electrons. Okay, so it's where those wavelengths are missing in the absorption spectrum, because that's where they've absorbed that energy. Okay. And of course, they correspond with the different amount of energies based on how many energy levels they jumped up and fell back down. Okay, so like if you see this right here, you've got the blue line was 2 energy levels, and blue light has more energy than red and green. So that makes sense. Okay, it's more energy. All right, so here is an example. The continuous spectrum has everything. The emission is what was emitted, so that's where the wavelength was absorbed, dropped back down, and the absorption is where they absorbed it and jumped up to the energy levels. Higher the color, the more energy it absorbed and then released. Okay? And if you hadn't seen the things yesterday, this might be more confusing, but at least this part should make sense, right? That's the colors you were seeing yesterday. This is called the stair-step model, and it's kind of, so when their electrons are absorbing and releasing, they can do so in a couple of different ways. They can go 1, 2, 3 at a time, or sometimes they can skip and go like that, or sometimes they can go all the way down. Okay, it just depends on how much energy is absorbed and released. Okay. This was the hydrogen spectrum, which was the one light I could not get to work yesterday. That's what it looks like. So that's the absorption one. Again, the colors are corresponding to how many energy levels they're jumping and falling. Some uses of that atomic spectrum that we looked at yesterday are these right here. And you should go ahead and write these in your notes real quick. They can be used to analyze unknown elements or compounds. Okay, so they're used in forensic science, astronomy, and environmental control. And of course, at this point in your life, you should know that colored fireworks come from different colored metals. If you don't know that, you'll get to see that in the flame test lab we do next week, which we will. We'll be burning samples that we know what they are, and we'll record their colors, and then you'll get some unknowns, and you'll try to tell me what your unknowns are. Okay, so we're going to make green fire, hot pink fire, pale yellow fire. We'll make some cool colors, like a reddish orange. Do what? You can, but a lot of times we're not melting them. They're going to be sticks that are soaked in these salts. So they're going to be sticks that are wet, but when you burn them, they burn the colors. Okay? Does everybody have that? They were just at the bottom where it says every element has a unique spectrum. That's a good place. Yeah. Okay. All right, I'm going to move on. If you didn't get it, look on to a friend's. And then, of course, we're going to see that in the flame test. So we talked about the Bohr model last unit, and we said that Bohr proposed that electrons are in specific energies called orbits, and he said that the energy of the photon is the differences in these energy levels. Okay, so that was the Bohr model. We also said that the problem with the Bohr model is that it only worked for hydrogen. Okay, so that led them to come up with a different model, which was, we'll talk about here in a second. That's just showing you the energy levels like we looked at last time, just to refresh your memory. That brings us to the quantum model of the atom. Okay, I told you were going to be confused today. I'm just kidding. That formula is just there to scare you. We don't use it. It's not barely complicated at all. Okay, so the quantum model of the atom. Okay, it says that electrons actually behave both as particles and as waves. Okay, so it's called the dual particle theory or wave-particle duality. There's a couple of ways that they call it. But basically, when electrons are interacting with matter, they're going to act like particles. When they're interacting with space or traveling through the air, they're going to act more like waves. Okay? Heisenberg, anybody have Heisenberg in here as their scientist? Okay. Heisenberg came up with this uncertainty principle that states that it is impossible to know the location and the velocity of the electron at the same time. I don't know why he got his name after that, because now we think of that, I'm like, well, duh, they're moving so fast and they're so small, how could you know both? But it is an important part of the theory, is that you can't know both at the same time. Erwin Schrödinger, found a very complicated equation, it's just this one that I put up there to scare you, and he determined the probability within 90% of where the electron is located. And these are called the orbitals.
Wasn't he also the cat?
He was the cat guy. The Schrödinger cat guy, yeah. And whoever had that, I said, you better make sure you put the cat. And he put.
It's like can be considered both dead and alive.
Yeah, like you put the cat in the box, and if you don't know, you can't. It's kind. Yeah, you can't know is it alive or dead until you open the box. Yeah.
You like put a cat in there with poison.
It's all about like probability.
Yeah, it's about probability. Yeah. Yeah. But look, if you don't know it, look it up. The Schrödinger's cat. Yeah, it's like a famous thing in science now. Yeah, and if you watch The Big Bang Theory, definitely in there. Okay. All right. So quantum model of the atom. Here is the pictorial of 90% probability. So it's close enough. We're going to go with it. And this is the currently accepted model. Is the quantum model or quantum mechanical model. So that brings us to what we really need to know. The most important part of this whole unit is the electron's address. Okay, and there are 4 quantum numbers that specify the address of an electron, and that is of course not an electron. That is a stadium. Okay, but if you go to a concert and you have a ticket to a stadium, you have your own little special seat that only belongs to you. Okay, so it'll tell you what level you're on, what section you're on, what row, and then your seat number. Okay, no one else has those same 4 numbers on their ticket, correct? They might have the first 3 the same, but their last one is the seat. That's your seat, nobody else's seat. Okay, it's the same way for an electron. The electron's quantum number is its seat, basically, in the atom. Okay, and so that's what we're going to talk about. Okay, here's the part where it gets confusing. Ready? Not really confusing, just it's a lot to take in, then we got to put it all together. The first quantum number is called the principal quantum number. And it is basically the energy level, so what energy level are we in, and the size of the orbital. Okay, the possible values are 1, 2, 3, and then I'm going to say ... up to infinity. Because in theory, you could have infinity numbers of energy levels. Okay, in actuality, at this current time, we have 7 energy levels that are known. They correspond to the 7 periods on the periodic table. Okay. I think earlier in the year I mentioned that the race was on to try to come up with element 119, which would give us a new period. So then that would be a quantum level number of 8 could be possible. Okay, but we're only going to use 1 through 7 because that's all we have right now. Okay, but in theory it could go up to infinity. Okay, maybe in thousands of years they'll have element 327. I don't know. Okay, so those are their possible values. It corresponds when we're doing this with the coefficient in front of it. So this is a 1s, this is a 2s and 3s, and notice how much bigger they get as you go. So this is energy level 1, so that would basically be only hydrogen and helium. They're the only things that are just in energy level 1. Okay. The angular quantum number is telling me what sublevel and the shape of the orbital. Okay. The possible sublevels are S, P, D, and F. Okay? In an energy level, that is the order that they fill. Okay? If you need help remembering the order, I have a very fun little saying for you. And it is, science is pretty darn fun. I came up with that myself. Thank you very much. Okay? So we signify this as L. I'm going to do it as a cursive L because if I do print, you'll think it's a 1. And their values can be 0, 1, 2, 3, all the way up to n minus 1. Okay? And remember, n could go up to infinity. Okay? We're only going to be worried about 4 values. And that is, and this is important, this is where they got a little confused last class period. If you are in an s orbital, your value for L is going to be 0. If you are in a p orbital, your value is going to be 1. If your electron's in the d, your value is going to be 2. And I bet you can't guess if you're f. 3. Okay? Those are the values we will assign for the second quantum number if you're in those orbitals, okay, or sublevels, okay? The magnetic quantum number tells us the orientation of the orbital within the sublevel, okay? Their possible values, and that's m sub L, is negative L to positive L. Okay? And that's because that's telling you where its spot is. Okay, and I'm going to show you some pictures in a minute. These orbitals have orientations around the nucleus, the XYZ axis, because remember these are 3D things, they're not flat on a paper. Okay? So S is a sphere. Let's see if it shows us. Not that one. Well, okay. S is not there, but S is a sphere. So it can only have one orientation around the nucleus because it's a sphere, right? You can only turn it one way. This is the example of the P. Okay, P has 3 possible orientations around the nucleus or the XYZ axis. Okay, so we said that if we're in a P orbital, okay, so we're going to put this all together now. Now, you ready? Okay. The one thing I don't have in here is this. I should have put a picture in this because we're going to go through this. Okay, so let's do there's going to be 3 kinds. I'm going to just do them all on this page to make it easier. Okay, so before we do that, I want everybody to look at the funny looking periodic table that I gave you that just has letters and numbers. Okay, so you're going to read this, and if you want to transfer some of this on your real periodic table, you can, like put it at the top. Okay, so according to that chart a while ago, we said an s orbital holds how many electrons? 2. This is called the s block. Guess how many groups are in there?
7.
Groups are up in 2. Okay, S1 goes in the first group. The second electron goes in the second group. Everything in group 1 is filling the first slot of an s orbital. Okay. Everything in group 2 filling the second slot of an s orbital. Okay? Whatever period number you're in tells you that it's filling the 1s, the 2s, the 3s, the 4s. Getting bigger as we go down. Okay? According to the chart, how many electrons does the p sublevel hold? 6. Over here is the p block. Guess how many groups are in there? 6. You're finally going to understand why the periodic table is arranged the way it is. Okay? So, again, each one, P1, everything in that group is filling the P1. They're filling the 2P, 3P, 4P, 5P, 6P, etc. Everything in the next group is filling P2. So it would be 2P2, 3P2, 4P2. That's everything in that group is filling that last electron in the same spot. Which, by the way, is why groups have similar properties, because they have a similar electron configuration, just bigger energy levels. Okay? All the way over here to P6, okay, which is the noble gases, okay? If you look at the chart we wrote down, how many electrons does the d orbital hold? 10. Guess how many are in the d block? 10 groups. D1, D2, D3, etc. Okay? However, remember Aufbau principle? It says lower energy levels fill first. The S's are lower energies. So if you notice, I'm in period 4 when I get to that first d orbital, but it says 3d. It doesn't say 4d. And that's because it's 1 lower. So this middle d group is always 1 less. We call it n minus 1, 1 less than the period number. Okay? And then F has 14 electrons, so these 2 little things at the bottom are 14, and they're 2 less. Because remember I said the F orbital doesn't even show up until the 4th energy level, but it fits in at period 6. Okay, fits in at period 6. So that down there is 2n minus 2. We read this like a book. Piper, when you read a book, where do you start? Top left, right? And then you go left to right. When you get to the end of the line, what do? You go to the next line. This is exactly how we're going to read this. So when we're reading this, we're going to say, and we'll find where our element is. Let's say our element is, vanadium, which is right here. I would go across and I'd say I'd fill up my 1s's, I'm going to fill up my 2s's, and I go over here and fill my 2p's, etc. Okay, so that's how we read this. So now we're going to do this together, and it's going to be clear as mud right now. Tomorrow it'll be clear as crystal. Ready?
No.
No.
Yes.
Oh, come on. We got this. Okay.
Plenty of crystals aren't clear, actually.
What about salt?
What about salt?
Salt's not very clear, it's not clear.
I meant like crystal glass. You can see
But
through
you just
it.
said crystal.
There's lots of...
I'll take your word for it.
Thank you. Okay, so oxygen. How many electrons does oxygen have?
16.
No.
Eight.
8 electrons. Okay? So, reading from our chart, what's the first thing that shows up? 1s. We always start electron configurations with 1s. Bottom up, right? Aufbau principle, build from the bottom up. 1s has 1 orbital, and it holds how many electrons? 2. 1 up, 1 down. So we have now filled 2 out of our 8 electrons. So we need to keep going. After we finish the period 1, okay, what comes after 1s? 2s. How many electrons? 2. Okay, I now have 4 out of my 8. I still have 4 electrons to put in there. I need 8 electrons, do I not?
Yes.
I've drawn 4. 4 minus 8, or 8 minus 4 is 4. I still need to put 4 electrons, right?
Yes.
Okay, I have now filled my 2s over here. What comes next?
3s.
No, look at the chart. 2p. 2p or not 2p? That is the question. Okay. How many? No. You didn't let my. How many orientations or orbitals are in a p? 3. So I'm going to draw 3 lines. 1, 2, 3. This is my 2p orbital. Okay. I have 4 electrons that I still need to add in there, right? But what did we say? According to Hund's rule, everybody gets what? An up before they get a down. So we're going to say, I've got 4. This is electron 5, 6, 7, and now 8.
I think I get some of
Okay, now I have put 8 electrons. Do I stop or do I keep going? Stop. I've got 8 electrons. Okay, so this is called its orbital diagram, orbital notation. This is the orbital. If you see the word orbital, it means draw arrows. So they're sometimes called orbital diagrams. Sometimes we say orbital notation. Now, the longhand notation, which means I don't have to draw the arrows, is this. In 1s, I have how many electrons? 2. In 2s, how many electrons do I have? 2. In 2p, how many electrons did I write? 4. This is its electron configuration. Okay, that's its electron configuration. Now we're going to assign our quantum numbers. Yes, we are. Okay, we're going to do for the last electron. Okay, where was our last electron? It was right here, right? Last electron, because that's the last one we put in there. Okay, the principal quantum number is your energy level. It's always going to be this, whatever number's there, because you're in that's the energy level you're in. We're in energy level 2. So we're going to say 2 for our principal quantum number. Okay? We got 3 more numbers to go. Okay? The next number tells me what kind of sublevel am I in. Am I in an S, a P, a D, or an F? I'm in a P. And what did I tell you is the number for p's?
1.
1. So it's a 1. Okay? The next number tells me which one of the p slots am I in.
It's orientation, right?
It's orientation. Remember, we said our 3 slots, we assign them -1, 0, and 1. So we are in -1, because that's where we put the electron. Now, are we spinning up or are we spinning down? We're going, yeah, so it's a, is it positive or negative half? Negative. So it's a negative half. Those are the quantum numbers for the last electrons in oxygen. Okay, now do your worksheet for homework. Just kidding. We're going to do some more examples. These are the quantum numbers.
I don't understand.
Okay? So that's now, the next example is sulfur. So let's do it again. Okay? How many electrons does sulfur have? 16. Now we have 16 electrons. Okay. 16 electrons. Okay? Find it on the chart and predict what it's going to end in.
Something.
Okay.
So 3 P's.
3p what? Count how many over it is.
You're asking the wrong guy.
No, I'm actually not. Count over how many times in the what 3p what? 4. It's going to end in 3p4. So we can say it's going to end in 3p4. So literally, we're just going to fill up everything until we get to 3p4, and then we're going to stop. Okay? So we always start with what, Piper?
We always start with S1. Or 1S.
1s.
But can I ask one quick question?
You actually can, yes.
Okay. Would it be wise to like write in
It would.
elements into? Oh, so it's
No, it would actually be more wise to write this on your other periodic table. Take less time.
very sure.
Yeah.
So, like, just write the top numbers. Yeah?
Yes.
Okay.
Okay. All right, 1s, how many electrons go in there? So up and down. After, read across, what comes after 1s? 2s. Up and down. Then we go across after 2s, reading across the book. We got the 2p's, and how many lines do I draw for 2p? 1, 2, and 3, 2p. Okay? I'm going to give everybody an up. Up, up, up. Down, down, down. After 2p, I'm done with that line. I go to the next line, and what does it tell me? 3s. And I have an up and a down. And then we said 3p comes next. And we said we're at 3p4 because we predicted before we went. So up, 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 and down. So this is ending in 3p4. So we would write now, that's our orbital notation. Now for our electron configuration is 1s2. What's next? 2s2. 2p6. Why am I getting bigger as I'm writing? Now I'm going to go like this. 3s2. Just for fun. We did it that way. 3p4. So that was our electron configuration. Now, last time we did our quantum numbers for the last electron. Do you want to do the last electron, or do you want to do a random one in the middle? Okay, we'll do last electron. Last electron again. Last electron. So this time our principal quantum number is what? Where did I tell you it'll always come from? Comes from right here. 3. We are in the third energy level. Okay? We are in a P sublevel, and how did we say P's are designated? No, 1. Okay? And then we are in -1, 0, 1. We're in the -1 position. And we're spinning down again. So -1/2. Okay? What time do we get out of here? Do we have time to do it? Today we haven't had time to do a more complicated one. I'm going to try it.
Uranium.
Not that complicated. We're going to do my favorite element. You want to know what my favorite element is?
Phosphorus.
Tennessee.
Hydrogen.
No.
Magnesium.
You won't show up.
Zirconium.
Is it,
Excellent.
E.
Okay, it's vanadium, and it's 23 electrons, and it's because my first name starts with a V, and I was born on the 23rd, so hello. Yeah, so that's why it's my favorite. Okay, all right, 23 electrons. Find it on your periodic table and tell me what you predict it ends in.
can we just write this like anywhere?
Yeah. Or you can just watch and see, so see if it helps you, just whatever. Okay, 3D what? Are you sure? Is it 3? I thought it was 3. So 3D3. The way he did that, it's in 3D and it's the third element in that group. Okay. So, do we want to draw orbitals? Yes, we do. Or do we want to just do electron configuration? Okay.
Actually, that's the water one.
1s, up and down. 2s, up and down. Then comes 2p. Or not 2p. Okay, after 2p, we read to the next line and we get 3s, up and down. Then comes 3p, up and up and up and down and down and down. And then after 3p comes 4s, up and down. And then comes 3D. How many lines do I draw for a d orbital? 5 has 5 orientations. 1, 2, 3, 4, and 5. So this is 3D. Requires less energy to fill the 4s. That's why we fill it first, and then we go to the 3Ds. And then 3D3, so we say up, up, and up. So we would write this as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. And that would be its electron configuration. Ask me after tomorrow, because I think it'll make more sense tomorrow. Yes, sir.
Okay, so there's 14 sections for the F's, right?
Uh-huh.
But there's 15 sections.
That is, some people put lanthanide and actinide down there with them. They're not really supposed to be there.
You
Some,
don't include lanthanide.
yeah, and we don't do a lot with the F orbitals. Okay, now let's do the quantum numbers for the last electron. What energy level am I? 3. For the sub-level, what did we say signifies a D? Hold on, 2. -2, -1, 0. 1, 2. So that's 0. And then we're spinning up, so half. All right, do not do your homework tonight. Don't even think about this tonight. We're going to clarify some more tomorrow.